All right, questions on anything else up to here? So we were talking about number theory, and we talked about Fermat's last theorem and a little bit about prime numbers. Let me say a little more about prime numbers, and then we'll talk about the things you need to do for your homework. And then we'll talk about the quiz, which is also on Friday. So how many primes are there? There's an infinite number of primes. How do we know that?
Because if you think of a prime, you can always make up a new prime.
Yeah? How?
So it would have all the factors in it. If you add 1 to it, that would not be divisible by any of the factors in that string.
Okay, so suppose P1, P2, up through Pn is the set of all primes, where n is some finite number. Right, so suppose there's not an infinite number of primes, then we could make a set containing all the prime numbers, and it would have some fixed number of elements, right? 10 gazillion, 519 bazillion, and 5, or something. But there's some number, right? So yeah, now set B equal to the product of all of those plus 1. And so B is not divisible by P1. How do we know that? Because it's exactly 1 more than a multiple of P1. It's P1 times this big long number plus 1. And similarly, B is not divisible by P2 because it's P2 times some integer plus 1. It's 1 more than a multiple of P2. And in fact, it's not divisible by any of these numbers in this set, because it's 1 more than a multiple of each of those. Well, if this is the complete set of all prime numbers, and B is not divisible by any of these primes, then B must be prime. Right? Therefore, B is prime. Therefore, B equals P1 or P2 or one of these numbers in here, because this is the set of all primes. And so B would be equal to itself times some big huge integer, and it's just ridiculous, right? So this is a contradiction, right? So B must be divisible by something, but it's not divisible by a prime, and that's a contradiction too. Yeah?
Could you say that because every non-prime number has a unique
Factorization?
Yeah. Of prime numbers, and there's an infinite number of non-prime numbers, that there would have to be an infinite number of prime numbers?
I don't know if that follows, does it?
Well, because there's only such a big number. If you multiply the set of all primes together, that would work for all the non-prime numbers up to that value. But if that were to be true, as you went into higher numbers, you'd need more prime.
So here's a set of numbers. It's an infinite set. These numbers get bigger and bigger and bigger. And if 2 was the only prime, I wouldn't have the contradiction that you're describing. Okay. Right? So it's possible that even though there's only 10 of these primes, that by taking powers of these and multiplying them, I could get to every number. Okay. It's not true. It's absurd, right? But it doesn't immediately jump out, I don't think. But I think you might be able to get to another proof like that, which would be interesting. So this was the proof known to the Greeks. Just multiply all the supposed primes, add 1, you've got a contradiction. Either this is prime, which is impossible, or it's divisible by something other than one of these, which means there's another prime that's not in that set. So there is an infinite number of primes, which is kind of cool, especially if you like Bitcoin mining or cryptography. So there's an infinite number, but we can ask a related question. How many primes are there less than or equal to any given integer n? So if we pick the number 1,000,000, how many primes are there less than or equal to 1,000,000, or 1,000,000,000, or 1,000,000,000,000? And we don't have an exact answer for that. If we did, we could use that exact answer to ferret out a way to generate primes, because we just keep increasing n until this number of primes went up by 1, and we'd know we had just passed a prime number. So there's no exact answer for this, but there is something pretty dang cool. So as n approaches infinity, the limit of the number of primes less than or equal to n equals, anybody know, want to take a guess? Have a crazy inspiration? Natural log of n. Ding, ding, ding. What the heck? So log base e, right? E is 2.71828, etc. Natural logarithm of n tells you how many primes there are up to n. And this works better and better as n gets bigger and bigger. For small n, it's not even close. And if you graph the number of primes less than or equal to n, it's not even a smooth function. It goes up in steps. And these steps generally get wider as n gets bigger. But every now and then you find a pair of numbers that are both prime. And so you'll find little runs like that in there. So it's a weird curve. But asymptotically, it's approaching natural log of n. And that's been proven hundreds of years ago. And this gets into some glorious mathematics. So if you want to lose yourself, do some Googling on the Riemann zeta function. I have a great undergraduate level text on this. Actually, this was written for high schoolers. That describes the Riemann zeta function and all the glorious aspects of it. But it basically starts from this question of distribution of primes, how many primes there are up to a point, but it gets into some incredibly deep mathematics, some big cache of unsolved problems in number theory and algebraic geometry and other areas. And it all stems from this very simple question of, does a number have any divisors other than itself in one? Right? Is a number prime? And it just launches into some really strange stuff, and a lot of this weird mathematics, you start exploring abstract notions and you strip away the specifics of integers or real numbers or functions, and you just make things more and more abstract. And every now and then you do this enough and you suddenly stumble across some property of subatomic physics or galactic interactions or something from the real world, and we don't know why this happens, right? So when I was doing my math degree, I was working in an area called mirror symmetry, and this is not on the exam. Mirror symmetry came from this question of trying to find roots, zeros, of these really, really big polynomials. So polynomials where each term had a degree that had 12 digits to it. So x to the trillionth something plus something times x to the other trillionth something, right? Ridiculously huge polynomials, and trying to find zeros of them. Find a value of x which makes this zero. It's almost impossible to do. You can approximate it, right? But to actually find a 0 for something bigger than a cubic equation or a fourth degree equation. There's no way to do that in general. And all of a sudden these physicists started publishing solutions to these equations. And if you have a number, you can plug it in, use a computer to do the algebra, and you can say, oh yeah, that turns out to make the whole thing equal to 0. It's easy to verify, very hard to actually find the zeros. Well, these physics journals started publishing zeros to these equations, and the math community was kind of like, what the heck? Where are you getting these? And they said, oh, well, we do this and this and this, and there's the answer. And it was absolute nonsense. Had nothing to do with anything. But some of these people had taken some mathematics and made some assumptions about what it was saying and then used that to come up with these roots. Well, they were coming up with correct answers, but there was no explanation for why they were correct. And it started this whole kind of area of algebraic geometry called mirror symmetry, trying to understand, because they were doing something based on physical principles, something related to string theory, and the mathematicians were doing something related to an abstract mathematical thing called a Calabi-Yau manifold, and there was some kind of connection. What you do over here relates to what you do over there in some weird way. There's some symmetry. So this happens a lot with mathematics, and Riemann zeta function is another area like that. And primes often seem to be at the center of a lot of this funny business, which we don't know exactly why. Since we're into weirdness, have you encountered that? Yeah, so e to the pi I is -1. So there's e, right, the root of the base of natural logs. There's pi, circles. There's the square root of -1. And if you somehow define what raising e to an imaginary square root of -1 times pi is, you end up with this nice -1. Right, that's a really beautiful but kind of bizarre relationship. And so this stuff pops up a lot. So prime numbers, like I say, they're kind of at the center of a lot of this stuff. So that's called the prime number theorem, by the way. And the fact that the number of primes asymptotically goes to log of n. That's the prime number theorem. Mostly you should know there's an infinite number of primes.
So you said that works better as n gets larger.
Yeah, it works horribly for small n.
But do people use that to like actually get to these really, really huge prime
Still doesn't
numbers?
work well enough to actually tell anything.
Okay, so you can't say like, well, we found this n and it's this digit, so let's take log of this many numbers. Did we miss one?
Right, and that apparently is, well, it may never work. So one of the open questions is this notion of twin primes. So 3 and 5, 5 and 7, 11 and 13, 17 and 19. These primes that are only separated by 2, and as far as we know, there's no point beyond which these cease to occur. And it's been explored in various ways, and the lower limit on how big we might have to get before these disappear is really huge. And if these things exist forever, right, you have no hope of ever having an exact formula for the number of primes unless it somehow takes that into account. So log's definitely not going to do that. But it can get you to some good places. So that's the twin prime problem. That's an open question. All right, let's talk about Fermat's little theorem. And this comes up on your homework. So Fermat's little theorem is the following. If p is prime and a is an integer and p does not divide a, so a is not a multiple of p, then we have the following fact. A to the p minus 1 is congruent to 1 modulo p. So as long as a is not a multiple of p, if a is a multiple of p, then a is divisible by p, so a to anything is going to be congruent to 0. But other than that kind of unusual case, if you take any number and raise it to the p minus 1, it's always 1 more than a multiple of p. And that's kind of cool. And we can use this to do some fast calculations. So let's do a fast calculation. Let's calculate 7 to the 221st modulo 11. So my A here is going to be apparently 7, and my P is going to be 11, and 7 is not divisible by 11, so I can apply Fermat's little theorem. So by Fermat's little theorem, I can just plug into here. I can say that 7 raised to the 10th is congruent to 1 modulo 11. And you get that for free without doing any work. That's just plugging into this theorem. Okay,
That would give you the same answer as 7 to the 221 mod 11.
Pretty close. Why?
What do you mean why? I thought that's what you did. You just rewrote the top to the bottom.
No. So I'm trying to apply this theorem, which says if I take some number and raise it to p minus 1, I'll get something congruent to 1 mod p. From my original problem, I know I want something mod 11, so I'm setting p equal to 11. And Fermat's little theorem tells me about raising some number to a power mod 11. Well, my question is about raising 7 to some power mod 11, so I'm just letting a equal to 7. But if I plug this into Fermat's little theorem, this is all I get. 7 to the 10th is congruent to 1. Okay, that doesn't tell me yet what 7 to the 221st is congruent to, but I'm pretty close. The benefit of doing that is if I take this and I raise it to any power, it's going to be congruent to 1 raised to that same power, and 1 raised to any power is just 1. So now I can do this. So 7 to the 10th to the 22nd is congruent to 1 to the 22nd, which is just 1, modulo 11. Well, 7 to the 10th to the 22nd, this is the same thing as 7 to the 10th times 22, which is 7 to the 220th. So with very little work, I've jumped all the way up to what 7 to the 220th is, mod 11. So now I have to do one piece of actual multiplication. 7 to the 221st is 7 times 7 to the 220th, which is congruent to 7 times 1, which is just 7. So a few lines on a piece of paper, I know that this thing is 7 more than a multiple of 11.
And why do you say congruent and not?
I can say congruent everywhere, because if things are equal, they're also congruent. I usually do. So 7 to the 221st is that. If I subtract 7, what did I say it was congruent to? If I subtract 7, I get this. This should be a multiple of 11. Right, and it is. It's a big multiple. So Fermat's little theorem is another version of being able to do these large calculations without a lot of work. So the other version we talked about last time was modular exponentiation, where we would calculate 7 to the 1st, 7 squared, 7 to the 4th, 7 to the 8th, keep squaring it, and then we just add up the squares that give us, add up the powers of 2 that give us 221. And that may be more work than this, but it's doable. All right, so let me glance at the homework. 'Cause I think we've gone through everything you need except, bless you, except greatest common factors, which we're going to do next. I gotta go to Canvas because I didn't save it. All right, so first one is on modular exponentiation. You want to do these in order. Okay, the warm-up is designed to ease you into modular exponentiation. So compute 5 times 7. I'll give you a hint, it's 35. Okay, and then see what that's congruent to mod 3, and then find what 5 and 7 are congruent, multiply, and so on. Do the same thing for addition. Do the same thing for multiplying 7 by itself a bunch of times, and by the time you've done those 4 steps, step 5 should have a pretty obvious answer. And then modular exponentiation generalizes this, so we're going to calculate this, mod 11, and there's the steps that basically guide you through the process. So have people done this already? Everybody's finished it. Awesome. That's great. Okay. So homework 6 is divisibility in modular arithmetic. So this was stuff that we already went over also. So find 5 examples of A and B such that A divides B. Find 5 examples such that A does not divide B. That's just playing with divisibility. Couple of proofs. Prove if A divides B, then A divides B times any integer C. We might have actually done that in class, but if not, use the definition of divisibility, right? If A divides B, then B is equal to A times some integer. And plug that into the fact that A divides B and see if you can show that B times C equals A times an integer. And it's easier than the proofs you've already done in chapter 3. Question 4, if A divides B and C, prove that it divides 2B plus 3C. And then question 5, just looking at some modulars and seeing if they're true or false. And 6, I think we actually did in lecture 2. So if A and B have the same remainder divided by M, prove that M divides their difference.
So in number 5, question 5.
Number 5?
And then I confused about C.
Yeah, so the negatives are a little strange.
So remainder not always positive, right? The remainder.
So we can say that, for example, 5 is congruent to negative 3 modulo 8, and this is absolutely true. Okay, because if we take 5 and we divide it by 8, we get 5 left over, right? If we take negative 3 and we divide it by 8, well, we get negative 3 left over. But we can also write negative 3 equals 1 times 8. Negative 1 times 8 plus 5. Right? And a way to tell if two things are equivalent is to see if their difference is a multiple of your moduli. So 5 minus negative 3 equals 8. That's a multiple of 8. So that tells you right there these are congruent. So that's true, yeah. So I can't grade that one, but I can grade all the others.
That's not one of them, though.
Oh yeah, that's right, I made that one up. Thank you. All right, and then the last one gets into greatest common divisors and Fermat's little theorem. So Fermat's little theorem, we already kind of did a lot of that. But anyway, play with that. So let's talk about Euclid's algorithm, greatest common divisors. So that's the last piece that we're kind of missing. And you'll use this in CSE 223 for your first or second programming assignment. So this won't be wasted knowledge. So, given two, I'm just going to say positive integers, A and B, Doesn't have to be positive, but there's all kinds of special cases if we allow negative. So let's just think about two positive integers, a and b. The greatest common divisor g, which we can write as GCD of a comma b, right, is the largest divisor of both a and b. So you've encountered this concept long ago, probably. When you're reducing fractions, you divide the top and the bottom by the greatest common factor. So that's all we're talking about here. What's the largest thing that divides both of a pair of numbers? And so we've got an algorithm for calculating these. So let's pick 91 and 39. Okay, so here's the algorithm we're going to use. Take your larger number and write it as something times your smaller number plus some remainder. In other words, do this modular thing. So 91 is something times 39 plus some remainder. So I think this is going to go in twice. That's going to give me 78, and it's going to have 13 left over. All right. So take this number and take this number and move them over. 39 equals something times 13 plus some remainder.
3 plus 0.
So 3 times 13 plus 0. Okay, once we get down to a 0, this is your GCD. So let's do 100 and let's make it a little harder. Let's do 30. So 100 equals 3 times 30 plus 10. Bring those over. 30 equals 3 times 10 plus 0. There's your GCD. That was a really uninteresting example. So someone give me another pair of numbers. 99 and 40? Cool. All right, so 99 equals 2 times 40 plus 18. 40 equals something times 18 plus a remainder. So 2 times 18 is 36 plus 4. 18 equals something times 4 plus a remainder. So that looks 4 times 4 plus 2. 4 equals 2 times 2 plus 0. There's your GCD. That's not a common divisor. What the heck did I do?
You did 98 and 99.
Yeah. That should
Yeah. There we go. Perfect.
Oh, that was a quick fix.
Yeah.
I wish I could do
Don't
that.
try that at home.
Can you do that on a quiz?
You can try. All right, so 40 is 2 times 19 plus 2. 19 is 9 times 2 plus 1. 2 is 2 times 1 plus 0. There's your GCD.
So we can do the long division first and to get remainder,
Mm-hmm.
and then so keep going.
Or use a calculator,
Yeah.
right? So if you have a calculator, so I always use BC-L. So I could do 99 divided by 40, and it's 2 with some stuff left over. If I do 99 minus 2 times 40, that tells me what the remainder is. And then you can go from there. And this should make sense because 40, we can factor that. It's 2 is 20, 2 squared will be 20, 2 to the third will be 5, so 40 is 2 to the third times 5, and 99 is
11 times 3 times.
yeah, 3 squared times 11. And there's no factors in common here, right? So if you write this thing out in its prime factors, you can sort of ferret out the GCD like that. But we don't have to factorize in order to find the GCD. We can use this thing, which is called Euclid's algorithm. And that'll get us the GCD right away. So if we have two numbers whose greatest common factor is 1, we can say those numbers are relatively prime. They're prime relative to each other in that they don't have any common factors. 40 is not prime and 99 is not prime, but relative to each other we say they're relatively prime. All right, you want to try some Euclid algorithms? I know.
Are we going up to the board?
Let's go up to the board and let's do your homework. Yay. And then you don't have to think too hard about it at home. So let's go ahead and work on these question 1s. And maybe I'll grade that one. You never know.
Right, come on.
Perfect number for Alright, so we, am I reading it out? You're reading it out. Okay. 150. 100.
What are you doing, Non? Straight
Second layer.
Alright, what's next?
Is 1,000. Five, 7,
Alright.
1260. 46. Then last set is 1001.
I love this so much. Stop.
The algorithm equals. Oh.
That would make sense.
What? No, be proper, bro. Sweet. That's 0 divided by 46. And then you say, well, so you just do 46. Plus 18. Quick, Ryan. How many times does 18 go to 46? Isn't it 3? Is that pretty good? Hey, it is. Well, I really like your enthusiasm right now.
Wow.
Which one?
That was on 192.
Oh, dang.
So it's 1 plus 494.
I think all of this is wrong.
Why?
He's just not writing the.
Playing it back.
But you don't know what the remainder is.
We had, well, because the constant doesn't matter. We don't care about the constant, so you divide it. And, no, you don't.
Constant, you break down the
Wait, what? I thought you brought down the remainder.
yeah.
Oh, you
Isn't that the remainder? Oh, you're oh. Wait, no, you might have been right. Wait,
No.
stop, no, stop, no.
I'm not gonna,
What was this?
Hey!
But now you've done the constant and the remainder. That's why we do it.
Okay, so right down 100 even.
I'm glad we went through that.
Alright.
Bingo.
1,286.
Something times 15.
What's bingo? What's the name? What?
3.
And you want that remainder on the end to be smaller than 15.
Oh.
I think.
Wait,
Wow. Here's your ego. Maybe I'm just better.
Come on, let's do it.
Why are you doing this? You only have to do this.
If you add,
What's that? Is this? So the first time you were working with.
I have this fear.
18.
You go under 8, now you gotta work here.
46.
But it's not up there. Can I show you something?
Wait, I'm racing
Feed him. Faster. No, feed him was to David. Faster was to David. I like to keep you both in the race. David, go David. Ryan, go faster. No, that's all I want.
Once you have 0, that's your GCG. That's the algorithm.
Use your hands, no.
You have to use your eraser head.
No, what's the head?
No. I'll do it in 3 seconds.
Like it. I like your name. Give me your name.
Wait, how many stats I work?
Okay.
Yeah. Wait, she's the one that's removing you? No way. No.
But it's still like it doesn't have the word plan option. Is this what it shows if I have the manual as our friend and I don't have it?
Oh my gosh. William.
I'm not watching it. It's like, that's why it's issued with one.
Alright.
I'm just really confused because it's such a roundabout way of doing it. They're not even blocked.
Wait, can you see her story?
Not
What is cute?
but I don't know if I believe it. Did it just run out?
We gotta do this.
Alright, what else? What are we doing now? The one that I haven't done, I
You
think.
can take a picture from it.
Where you going?
No, we haven't done that one.
I know, because we
Oh. Hey. Yeah, this looks like it's a pretty solid explanation.
What happened?
You can take a look right here.
Oh, cool.
Oh,
1260 and 46.
this is so.
Such a weird way.
This is so weird.
Such a weird way.
I see.
Do you want me to hug you?
No, I don't need a
I
hug.
feel like physical.
27 times
No,
46 plus 18.
I'm not actually that affected by
2
it.
times 18 plus 10, good. 18 is 1 times 10 plus
I'm still more
8,
affected by
good.
the PA one.
10 is
Hey, I just want
1 times
we're taking
2.
It's his.
Okay.
because I really want. Oh wait,
Let's see. Oh no, you broke double marker.
Yeah.
Sorry.
Oh, so
Wait, is it 1260 45 or 46?
It's both.
Oh.
You really should draw more arrows, Caleb.
something 2 plus something.
Yeah, Caleb, traverse that link first.
0, that's so yeah, it helps to stick to and you can check your answer afterwards, and 4 does not divide 46.
So,
Get the homework up again.
I wrote mine.
so the last one that you got from here.
But it was
Basically, yeah.
I have a lot of it.
126.
Because I wasn't checking. Anyone where I had to check or something. I was also messing up because I was thinking Union was supposed to be only the things that I didn't realize that it was just like printing everything without repeats. I was like, I already have a function for no repeats. So it was just like, put it together, run it through my no repeats, and there it is.
What is
So
28?
3 lines.
That one. 28 does not divide 45.
For these two, multiply equal that.
1, 2, 3.
So that's like the 30 minutes ago, so then it's.
Why is it 28 instead of 45?
Oh yeah, it's 45, it's not 28.
So you have like personalities.
That's a special case. We'll talk about that in a second.
And then I actually did.
All right, so I think everybody's got GCDs down.
I ran it through that and then for the no repeat, so I can see that no repeat.
No, because normally you would bring down the 28, you could bring down.
Even if they're really short.
No.
Well, I mean, I
No.
All right, so grab a 5-minute break if you want, and then let's come back and let's talk a little more about some applications of all of this stuff. And write down your answers for your homework so you can, like, unless you want to do it again.
I'm just gonna take a picture of the answers, but Go back.